In a descent, the disposition of the four forces, lift, weight, thrust and drag, will depend on how much power is used, but in all cases the lift vector is inclined forwards with the aircraft in a nose-down attitude. And the weight vector, as in the climb, can be split into two components. One, W cosine gamma, where gamma is the angle of descent, acts perpendicular to the flight path and is balanced by lift. And the other, W sine gamma, acts forward along the flight path and adds to the thrust, which is reduced for the descent. This added component restores the thrust-drag balance. If the nose of the aircraft is lowered with a constant thrust setting, the increased forward component of weight acting forward along the flight path will cause an increase in IAS. This increased IAS will result in a rise in drag, which will eventually balance the weight element, at which point equilibrium is restored and the speed will stabilise. If the throttles are closed, the thrust force is removed, and a larger forward component of weight is required to balance drag and maintain a constant IAS. This is achieved by lowering the nose of the aircraft to increase the descent angle, gamma. To sum up the arrangement of forces in a descent, lift is less than weight because lift only has to balance the component of weight perpendicular to the flight path, W cosine gamma. And thrust is less than drag because weight is giving a forward component in the same direction as thrust, W sine gamma. The total reaction of lift and drag opposes the weight vector. There may be emergency situations, typically a pressurization failure at high altitude, in which it is necessary for the aircraft to descend as quickly as possible. The high rate of descent necessary can be achieved by several means, which are usually used in combination according to the circumstances. The first action would normally be to close the throttles to minimize thrust and simultaneously lower the nose to initiate the descent. Drag can be increased by extending speed brakes or spoilers, and if the speed has to be kept low, say with structural failure or an unlatched door, the landing gear and possibly the flaps can be lowered as well, observing the appropriate limiting speeds. If there are no speed restrictions, the gear would be left up and the nose lowered to increase the speed up to the limiting IAS, VMO, or Mach number, MMO. If the initial limit is MMO, then IAS will be increasing as the aircraft descends, and at some stage the nose will have to be raised to keep the speed from exceeding VMO. The rates of descent achieved in an emergency descent can be quite high and would require a fair amount of anticipation by the pilot to level off at the required altitude. In a glide, that is, a descent without power, there is no thrust to provide the propulsive force and balance the drag. This is done by the component of weight acting along the flight path. In a glide, there are only three forces acting on the aircraft: lift, weight, and drag. The forward component of weight, W sine gamma, is a product of the descent angle gamma. The greater the descent angle, the greater will be the forward component of weight. This component must balance drag for the aircraft to be in a steady glide. It follows that, if drag is reduced and lift remains constant, the required balance of forces can be achieved at a smaller descent or glide angle. The angle of descent in the glide is a function only of the lift-drag ratio. The angle will be at its least when the lift-drag ratio is at its greatest, which is at the optimum angle of attack, which in turn corresponds to the minimum drag speed, VMD. It is important to remember that at speeds above or below VMD, the glide angle will be steeper. So, the maximum distance in a glide will be achieved when the aircraft is flown at its maximum lift-drag ratio at VMD. The maximum lift-drag ratio is independent of weight. Provided the aircraft is flown at its optimum angle of attack, The glide angle and the still air glide distance will be unchanged, whatever the weight. However, the speed corresponding to the optimum angle of attack, minimum drag speed, will change with weight. VMD increases as weight increases. A higher weight would give an increased forward component of weight, and the aircraft would accelerate towards the higher VMD, with lift increasing and drag increasing until it balances the higher weight component. Equilibrium is re-established at the same maximum lift-drag ratio, but at a higher IAS. At a higher weight, the aircraft will glide the same distance in still air, but at a higher speed, and consequently the rate of descent will be higher. The glide angle will determine the distance that the aircraft can glide for a given change of height. This distance would only be achieved in still air. If there is a wind, the ground speed will be affected, and so the distance will change. In a headwind, the ground distance will be reduced. And in a tailwind, the ground distance is increased. The maximum lift-drag ratio of an aircraft will only be obtained in the clean configuration. Extension of flaps, spoilers, speed brakes or landing gear will reduce the maximum lift-drag ratio and give a steeper glide angle, thus reducing glide range. The minimum rate of descent in the glide is obtained at the indicated airspeed, IAS, which requires minimum power, VMP. Flying at VMP in a glide will enable the aircraft to stay airborne as long as possible, but will not result in the shallowest glide angle or best glide range. As shown in the graph on the screen, VMP is a lower IAS than VMD. Wind speed and direction have no effect on the rate of descent. One way of portraying the relationship of VMP and VMD is shown in the diagram on the screen, which is known as the whole aeroplane CL/CD polar curve. This lesson concludes the topic of descending. The next lesson continues with the flight mechanics of turning.